Hey everyone. So last time we finished up proving this theorem that phi is a tautology exactly when phi is valid. And in doing so, we proved another result that you probably won't understand yet, but should make sense to theoretical computer scientists, which is that validity is decidable. Decidability basically just says that there's an algorithm to compute something, and the whole point of doing this proof was to show that I had an algorithm to compute the validity of statements. So now we have sort of two definitions of truth, right? We've had these sort of like two competing definitions of truth. We have this syntactic definition and this semantic definition. So the syntactic definition unravels the syntax of the statement itself to determine the truth of the statement. Whereas the semantic one considers the possible worlds in which the statement is true, and if a statement is true in all possible worlds, then we consider it true, right? These are two definitions that, as you saw in the last video, are almost identical, but are motivated from completely different angles of solving the problem of defining truth, right? So what we'll see is that progressing from here, we're going to continue to define these two separate notions, the syntactic single turn style and the semantic or the model theoretic double turn style. But they're not going to be as similar moving forward, or rather, let me say this, they'll always agree, but they're not going to be as similar moving forward from this point. So with that out of the way, let's talk about the first thing we want to tackle today, a theory. Okay. And the idea, the motivation behind this is simply that the whole point was to study theories. Like, I might want to study Euclidean geometry. And if I ask you, what is the theory of Euclidean geometry? That's not a question I think that you can easily answer, right? You could think about it, and you might say the points, the lines, the planes that make up Euclidean geometry, but that's the model. That's a model of Euclidean geometry, right? That's the object that satisfies the axioms. The theory is actually better stated to be everything true in Euclidean geometry. The theory of Euclidean geometry is all the theorems you prove. And what are theorems but just sentences? So what is a theory but just a set of sentences, right? So that's actually the angle we're going to go for. So we'll say that sigma is a theory if it's a set of sentences. Okay. And there's two different things that we could be considering here. So like sigma, sigma is just any set of sentences. So sigma might be just like the axioms of a theory. That's legal. That's a set of sentences. Or it might be literally everything true, like all the axioms plus all the theorems. And both of these are fine. For now, we'll just consider sets of sentences. We'll distinguish these two ideas later, having, the difference is one set is very small, almost as small as possible, and one set is as large as possible, right? So we'll talk about that distinction later. But for now, we'll prove some things that apply to both, sets of axioms and maximal theories in and of themselves. So we'll just consider this definition beginning with a set of sentences, right? And now the most important first goal we have is extending the definition of a model to handling sets of sentences. And it's a very simple extension. It's exactly what you would expect. So we'll say that A models sigma exactly if I might need to go to the next line. So if for every sentence in the set, A models that sentence. So it's a very simple definition, right? Like we just if we have a collection of two sentences as the theory, then a model is a model of the theory if it's a model of both of those sentences, right? This definition, not too difficult. Yeah, it's exactly what you expect, and that's why the first goal was to establish what it means for a model, which was a lot harder. We had to do that recursive definition, right? It was a lot harder to determine what it means for a model to model a single sentence. But once we have such a notion, it's very clear what it means for a model to model a theory or a set of axioms or whatever else. It just means that it models each of the individual sentences that we're considering. Okay, so what's our next goal? Well, now we have a theory, but what do we want to do with that theory? Well, we want a notion of, we want some notion of phi is true in sigma. We want to develop some, formal notion that intuitively says this. And as you might expect, there's two approaches. One, we'll develop this notion, and two, all right, let me use different colors. So one, we'll develop this notion, and two, we'll develop this notion. And one, unsurprisingly, will be syntax, and the other over here will involve semantics. This tends to be a recurring pattern that we'll develop these two notions, and then of course we will prove that these two notions are equivalent. Exactly as we did. You can view this as sort of a repeat of the first couple videos in this series, but now considering sets of sentences rather than sentences themselves. So both of these notions will attempt to capture the idea of phi is true in sigma. We'll begin. We're 7 minutes in, so why don't we start with this one? Because we'll actually handle both in this video. But let's define the semantics one first, because it's far simpler. So, all right, so our definition here is, we will say sigma double turnstile phi if for every model A, I like doing gold for the variables so it's more clear. A models sigma implies A models phi. So basically what this is saying is that we'll say that, and why don't I introduce the English word we'll use for this? So equivalently, phi is a consequence of sigma. Okay? So the idea is, right, remember, models are objects that exhibit the set of sentences. So if A is a model of sigma, that means A is an object in which all of the sentences in sigma are true. If it happens to be the case that implies that A is a model of phi, what that means is that phi is another sentence true of the model A. So importantly, or rather, what I'm saying is, importantly, what that means is every model, every possible world of these axioms sigma, in every possible world, phi is also true. So in one way, it's very clear to say that means, phi is true given that sigma is true. But of course, there's no proof of this, right? So from our world, and this is when this gets extremely meta. So from our world, standing outside looking in, we can see that phi is true in sigma, because sigma may be establishing many possible worlds. However, regardless of the possible world you live in, phi is always true. So clearly, phi can't be false in sigma, right? However, this doesn't actually mandate that we prove that phi is true. So sigma, not yet. And in fact, it will be the case that sigma is able to prove phi is true. But for now, all this definition says is that phi is true. Phi is like a true statement, considering that everything in sigma is true. And actually, that will be this distinction between the semantics and the syntactics. Semantics will say, I know for sure that phi is true. And the syntax will say, well, I know for sure that phi can be proven. And uniting these two together gives us the notion that true statements are provable and provable statements are true. This sounds like such an obvious thing that you would think you don't need to consider it, but in fact, you do, right? Like I mean, we're trying to develop a theory of proof, so I don't know. That's important that we develop. So I mean, we're going very, very foundational, but this is an important thing we develop. Okay. So moving forward, another definition. And this is a syntactic definition. So it'll look very familiar. We say phi, and then remember that picture I drew a while ago of syntax and semantics, we're now on the other half of it. So we'll say that phi, and this will be read as phi is deducible from sigma. Oh. All right, sorry, I messed it up. Here we are. Okay, so we'll say phi is deducible from sigma. And now, remember, the notion we're trying to capture here is a proof. So remember, in the first time we went through this all, and we talked about validity and tautology. Validity very mechanically used models to just, it just used models to determine which statements are true. And then tautology provided sort of an algorithm for checking the validity of statements. So that's what this will be. This will be an algorithm for checking the truth of phi, considering that sigma is true. And of course, what that means is we will say that sigma deduces phi exactly when there's a proof of phi in sigma. So why don't you pause the video for a moment here. How would you formalize the notion of a proof? What does a proof formally look like? And how can we say, because ultimately what we want to say is, we'll say this: if there exists and then a proof, right? How do we formalize what a proof is so that we can argue that one exists? So yeah, pause, take a moment, and then you'll get the answer when you come back. Okay. Well, the idea is, a proof will be formalized as a sequence of sentences where all the sentences are true. That's the idea. So, a sequence, phi 1 through phi n, right? So this is just a sequence. The point is this is a sequence of true sentences. That's the worst where I think I've ever written. So where, and then here's a few properties I wish the sequence to have. Well, for one, the proof should actually prove what I want. So the last statement in the sequence, the last line of the proof, better be the thing I'm trying to prove. Okay, that's one thing. And now we want to make the argument that everything written in the proof is sound, that every statement is, to some, I'm speaking intuitively, but every statement is true. So it has to end with the consequence, and for all, I'll abbreviate for the sake of space. So for all psi I, one of these things is true. Let's begin. So one possibility is psi I is a tautology. Okay. Yeah. Like if I write down a tautology in my proof, no one's going to argue with that. And in fact, right, that's the whole reason. Like the idea is, that's actually the whole reason behind the notation. Really, what a tautology is this, right? A tautology is precisely a sentence that can be proven with no premises. Okay. Actually, this is not obviously true. Once I've written down this definition, maybe you can prove that a tautology is exactly that the tautologies are exactly the sentences deducible with no premises. Okay. And then so one possibility is that psi I is a tautology. Or another possibility is that psi I is just an axiom. And then the final possibility, and we'll formalize this, or there exists a j and a k, both less than I, such that phi of k is actually the statement phi j implies, I'm saying phi every time, god damn it, psi k is actually equal to the statement. I'll put parentheses around it so it's clear that this is one statement. So psi k is actually the statement psi j implies psi I. Okay, so what will this actually look like? Well, first of all, before anything else, this is Modus Ponens, right? This is given that I know psi j is true, and I know that psi j implies psi I is true, I'm allowed to write down psi I in my proof. So what a proof might look like is phi 1, phi 1, and then, oh, here's phi j, and then, oh my god, here's the statement phi j implies phi I. So that means I'm allowed to write down phi I. That's a legal sequence in this proof, right? So everything in this proof is either a tautology, so always true, or we're assuming it to be true, or it's implied by things we've already proven to be true. Okay. So I think that's the definition. And that's a little bit of a hard one. So I won't do it now, but my next video will be 5.5, and it will be it'll actually be a pretty difficult example of a proof of like constructing a formal proof of something. So that might actually be worth taking a look at. So moving forward from this, we now have this definition, and we have this definition. So what we're gonna hopefully show is that, or eventually we're gonna hope to show this statement, which you'll notice is extremely similar to the completeness theorem. So that will be the goal of what we aim for. So we're at 19 minutes. I have Anyway, this will be later on though. We'll prove this, which is what we would hope, right? That all true statements are provable. There might be two things you're concerned about. So first of all, I just said all true statements are provable. I just said all true statements are provable. And That's like, you might have heard of like Gödel's incompleteness theorem. I promise that that's not like, if you have heard of that, you're like, oh, it's maybe, hey, all true statements aren't provable, but for right now they are, because we're working in propositional logic and working with just basic Boolean logic. When we get to, we'll distinguish completeness, because of course, famously, Gödel's two most famous theorems are called the incompleteness theorem and the completeness theorem. So there's actually a lot of distinction between whether we're working. When I say all true statements are provable, am I talking about a theory or am I talking about logic itself? So don't worry about that. That's what I'm saying. I just figured that might be a concern. The second thing is a lot more interesting. I'll try to make this quick because this is just intuition. But that's one. I'll actually erase this to give myself a little bit more space. So two, is Modus Ponens actually enough? Okay, so I only allowed you tautologies, axioms, and modus ponens. If you are familiar with logic, you may have seen, the law of the excluded middle, that not x, the law of the excluded middle is like this. You might have seen other forms of, and in fact, if you've just done any math, you've done proofs by contrapositive and proofs by contradiction and, proofs by cases, and all of these are not proofs by modus ponens. So why is it that I was allowed to define a proof using only modus ponens, and I didn't have to consider the other things? Well, first of all, we will. First of all, the first thing I want to say is that, remember this claim I made. Well, this basically says modus ponens suffices. Because if every and it's not the if and only if, it's this direction of it. So if all of the statements that are true in all models can be proven using modus ponens, this is strong enough, right? I've proven every statement is the idea. So the answer to the question, is modus ponens actually enough, is yes. Because we will prove we'll prove, like when we prove this statement, I'm just observing, and I'm not going to bring this up again even then, but I'm just observing that once we've proved this if and only if, we are in effect saying, yeah, the formal deduction system that I set up, because of course, this was just a definition. You can define your own formal deduction system if you didn't like this one, right? But the point is, this formal deduction system that only relies on modus ponens, we will prove, when we prove that every true statement is provable, in essence, we've shown that, yeah, modus ponens is really all you need is modus ponens, right? That's one way of looking at this. And I'm sorry, this isn't important, but when I was personally learning this was something that I thought a lot about. I was like, why is it that, like, how did we possibly get away with just one rule of inference? And intuitively, though, the answer is this. It's because we took every tautology as an axiom. You may have seen other proof systems of logic, and these are like axiomatic proof systems, basically. And really what we did was an axiomatic proof system. However, we took every tautology as an axiom. So, for instance, this sentence is a tautology. So this is one of our axioms. And this lets us do a proof by contradiction, right? Because I can prove, if I prove that not x is false. I've proven that not x is true, and then I can apply modus ponens to show that x is true. Another example, I'm running out of space, so I'll write it up here, but another example of a tautology is not y implies x implies, or not y implies not x, if and only if x implies y, right? This is a proof. This right here is a proof by contrapositive, right? And of course, what I've just written here, you can do the truth table and check that this is a tautology. So I'm just making this distinction because you may have seen other systems, right? It is an interesting question. What is the minimal set of axioms you can get away with, right? So I got away with one rule of inference, but I also took, I theoretically just took infinitely many axioms, right? I took every tautology as an axiom. You can deduce tautologies from other tautologies, right? So you can get away, and I don't want to say this for sure, but I'm pretty sure you can, I'm pretty confident in this. You can get away with a finite set of axioms for this. Like, you can presume only a finite number of tautologies and use that to prove every tautology. But for us personally, who we are not in the land of axiomatic logic, we are trying to develop model theory, and it's no weaker to take every tautology as an axiom, and it doesn't change anything. Because, of course, as we've proven, every tautology is true in every model. So I'll never be sad that I assumed a tautology to be true if I'm working in model theory, right? So that's a lot of distinctions is why it seems like it seems like I cheated and I somehow, even though there's a billion rules of inference you learned in logic, I only took one of them, and then I say that is enough to prove everything. But really, the strength is the fact that I'm allowing any tautology I'm allowing any tautology in this proof system, right? Okay, so anyway, I know that last 7 minutes there was kind of rambly and not too important, but this was a question I wanted to answer. That why is it fine to only consider modus ponens? And it was this is actually very similar to an earlier thing we proved, or we didn't prove, but an earlier thing I claimed, which was that and not suffice for every and not suffice for every connective. So I only need to think about and not when I do my inductive proofs. Similarly, when I'm thinking about these proofs, these created and deducibility, because tautologies and modus ponens is enough to prove everything, all I'm going to need to think about in my proofs by defining it this way is just modus ponens, right? Or, if I talk about what's a proof, I don't have to think about all the possible techniques you could use. I just have to think about the only technique you can use is modus ponens, right? So it just simplifies. Maybe it's inelegant to have assumed every tautology as an axiom, but it's no different for our purposes, at least when we're studying model theory. And it's going to make all the proofs easier because I only have to define modus ponens. Okay, so all right. I know that ending was rambly, but that's an important thing I wanted to get to say. Next video, I'll be doing an example proof using this formal deduction system, just to show you how it would work, and also further convince you that modus ponens and tautologies will actually end up sufficing to prove every statement we would ever want. Okay, well, thank you guys for watching, and I'll see you guys next time.